I guess I need to use Zoom to share. Yeah, the book. What do you find?
You may be drag the video. This.
Okay, yeah. My problem is more Zoom. Of the screen, okay, now.
Eso no está fatal porque es igual la descripción.
Are we on? I guess. Start. So,
Yeah, this wasn't 1%. Okay.
these feelings.
Yeah, so it's
Okay, so we've talked about it a bit already at lunch. I'm going to give a rough introduction to what openPMD is. I have a rough sketch for what I'm going to show in the coming hour, but if you've got any questions or want to talk about anything special, then just interrupt me. Just the way it's been working for the last days. Yeah, so one of the motivations that also René was talking about in the lunch break is kind of communication between different codes. Here's an example. If we talk about accelerator modeling in this example, then one workflow that you might want to have is to not have one large monolithic code that knows itself and nothing else, but instead have single stages that implement various single tasks, and also have common standard or a common language. Or for that, you need a common language in order to have, for example, the visualization, understand the data that you are creating, or just to have a common language to bridge these heterogeneous models. And one, not the only answer to this, but one answer to this is the openPMD standard for PMD is for particle mesh data. I guess in this round, I don't really need to talk about what particle mesh data is exactly, but let me quickly go over it from the perspective of particle simulations codes, plasma simulation codes. Particles and meshes are natural language in which we converse. Going a bit more high level because openPMD is not exclusively a plasma standard. A mesh basically is structured data and particles are unstructured data. Mesh is typically something like an n-dimensional space. So what you see here is these little boxes. In the terms of plasma simulation, something like the temperature mesh. So you have scalar values, electrical fields where you have vector values, and the particle data is then are then single objects that are within that discretized space, given really just as a list of their positions and then further optional properties, which are basically which you are free to define as you need them. For example, some things that you can pick on GPU are the charge and the weight. Now, taking this rough idea of what particle mesh data even is and transferring it into a data standard, this is the hierarchy that openPMD uses. So openPMD is not implemented in one specific file format, but the standard talks in terms of hierarchically organized groups, in terms of n-dimensional arrays that contain your actual data, and in terms of lightweight attributes which define your physics in such a way that someone else who comes across your data set somewhere in the forest doesn't need to go to you and ask you, hey, what's this actually? But ideally, the data set is self-describing and can be understood by anyone who reads it. So the top layer is serious in the sense that an openPMD data set is a series of iterations. Iterations that can be time steps in a simulation, snapshots, checkpoints. So the terminology that we use currently is iteration, but we're actually considering changing the name to snapshot because it's more generic. These iterations can be modeled in different ways. So if you imagine that you're running a very long simulation, you might not want to put everything into one single file, because if somehow your file gets corrupted, then things might go south, or just some data packets might just not scale if you put eternally just more iterations into them. So one thing that you can do is to put one file per iteration. That's what we typically still do in Click on GPU, or that you reuse files. That's just putting actually into one file. And talking specifically about ADIOS, we will see this later on in the practical examples of this. I'm currently just giving a rough overview on what I'm talking about, and then moving on to some more practical examples and live demonstrations. What ADIOS does is it has an abstraction for how a typical simulation code's I/O workflow works, which is called steps. So I/O happens in steps, and they correlate with simulation steps, for example. So you write one step, and then you say, okay, this step is now finished, and then this step is in a somewhat atomic way, meaning that you have not, for writing an n-dimensional array, for example, you have maybe your E field, and this E field is not only one n-dimensional array then in that sense, but it's an n-dimensional array that exists in several versions, several steps. And so this ADIOS specific feature is a third option on how you can model iterations. Yeah, that's about this. So let's maybe look at an example here in terms of HDF5. So this is a data set that was created by Pick on GPU. Here we have time step 100 that was written, B field and E field. E field is, for example, defined by its X, Y, and Z components, because, as I earlier said, it's a vector field. So what you especially need to pay attention to is that there are two levels of dimensionality. You have a three-dimensional grid, and within that grid you have vectors that are defined by their X, Y, and Z components. So you have an X dataset, Y dataset, and Z dataset, and each of these are three-dimensional. In terms of charge density, energy density, those are scalar values, so you don't have that last level of indirection. Particles, the simulation has electrons and ions, and I've unfolded the ions here, so they're defined by their positions mainly. Additionally, for numerical reasons, also the position offset, so that you can actually have a precise representation of floating point values with a very high value, which floating point numbers normally don't give you. So what you do here is integer plus a position. Yeah, and then further properties like charge, mass, and momentum. Particle patches, also René explained earlier, because we talked about this before the break, because you just write a list of particles, how do you recover any kind of structure? The idea is at writing time, you can additionally, it's not required, you can define, okay, I'm writing this patch of particles now. And this patch of particles was written by maybe 7th GPU, which was computing in this portion of space. So this patch of particles is located within this area in order to recover some kind of information back from this. This is basically the same thing in green. So this time ADIOS backend.
Could you maybe go back one slide and explain very short the right side you saw?
Oh yeah, I forgot this one, thanks. Here on the right-hand side, we have the an excerpt of some lightweight attributes. Now for the charge density. And as I said earlier, this is where you explain your physics and what things actually mean. So the axis labels, it's in a way a trivial thing, but it's still good to have to know, okay, which dimension is actually which axis. Then you want to know maybe what are the dimensions of my grid. So here you have clearly defined in reference to the global grid, where does this particular mesh, where is this positioned? What is the spacing of the grid? Unit SI, you see it twice, the grid unit SI and unit SI. But maybe let me begin with the unit dimension. That's our unit system. So units are defined in relation to SI units, but normally in a code you will not directly use SI units, but something custom. So additionally with this unit SI, you give a scaling factor that can use to convert your units back to SI units. In this case, Beacon GPU uses a scaling of 340,000. Yeah, so this is just for one mesh. We can later in the practical demonstration look at more things.
So what is prescribed now by openPMD? What is customized by the code that is using the data? That is using or writing the data?
Custom is the field smoothing. In this case, the field smoothing. All the other things are prescribed, though data order is deprecated.
Okay, so the right side is metadata, and the left side is sort of the hierarchy of the HDF5 line.
Exactly, and what we are not seeing so far is an n-dimensional array.
Okay, but all these names in the HDF5, how they are named, this is custom, can be customized. This is not something which is already given by the standard.
So what is given by the standard are the names of these attributes, for example, but if you're talking about the names of what does E or I stand for? So this is something which is then domain specific and has to be defined by your custom domain specific extension.
So technically this is like similar to like an input file. So you have the hierarchy and then you have to define each.
No, that's actually the output produced by the GPU.
Can you explain what this unique dimension? I could not understand what zeros are. You said that multiplied by something.
So this was now looking at the electrical field. So you have to give somehow a way that is even understandable for a computer to know what these units are precisely. That's based off the SI units, so the 7 SI units, length, mass, time, and so on. So that defines your actual physical unit. But let's maybe very trivially assume we're writing something metrical, so a length, but we're not actually writing meters, but we're writing kilometers. So in order to still have this representable in openPMD, you would then define the unit SI as 0.001 as the scaling back to meters to the actual unit, the actual SI unit. Because it's just your fancy that your code does not compute in terms of meters, but the numbers that you have in your code are kilometers.
So you give this area of 7 entries, and these 7 entries belong to they correspond to the SI units.
Exactly.
And you give some factors, for example, 1,000. If you're writing kilometers instead of meters, you're giving 1,000 or 1,000. I don't know exactly how.
1,000.
Exactly, unit SI is vector to convert, and 7 units is the potential. So it's meter to the 10 to the power of 1.
the first is the simplest to understand. If I use centimeters instead of meters, what that number would be?
100. No,
It's-
centimeters. Converting
No, it's 1 here in,
that-
in a unit matrix, you add 1, 0, 0, 0, 0. This means meter times 10 to the power of 1, therefore the 1. And this is then only giving you an information about the unit used. And then you need to know, okay, what was the simulation writing? The simulation is writing centimeters, so assume you have something like once a value in your grid of 1 centimeter, so simulation is writing out 0, is for example writing out 1. And then you need to give a conversion factor to convert your data from the grid into meters. So you need a unit SI will be then 100.
So they are two different things. One is the unit where you define more or less a derived unit by just giving these exponents.
Yes.
The SI unit, and then you have another field where you more or less give if you were using centimeters instead of meters.
Exactly. So in Picon GPU, for example, we have our own scaling because we do a lot of stuff in single precision as much as possible. But this would be not stable if we would run all calculation in SI units. What is the easiest one? We run meters and everything, but it could be Picon GPU is doing an astrophysics simulation, so we have maybe cells of kilometers or more. And it could be we run our small version where we have a micrometer or much smaller cells. And it's up to the simulation. The simulation is in writing out whatever the simulation has as data in. So it is, if we are running everything in nanometer, we write out nanometers, and then we give for the output a conversion factor to bring it into SI.
So
To the base units of SI.
centimeters is -2 or 2?
No, so wait, the first, this unit dimension is only, say, if you define it to 1, 0, 0, 0, 0, 0, 0, this means we are talking about the length. That's all the information that is in there. And if you additionally want to know, are we talking about centimeters, kilometers, miles, meters? So it's about the scaling in relation to the SI unit, which is meters.
Yeah, SI.
That's then the unit SI. So centimeters is the question. You would then put the unit SI as 100, scaling in relation to meters.
Yeah, but it's not power.
Yeah, but
Yes, the power would be, for example, if you are talking about an area, square meters, then you would put 2. Yeah, because it's meter to the power of 2.
I understand. Okay. And the unit SI is also a 7-dimensional vector for all the points.
So for the,
no, this is not 7-dimensional because we have a scalar value you would like to bring into whatever unit you have in SI.
But if I have a unit which is in centimeters per hour or whatever, then I have to two different factors, one for the time, one for the
Temperature is kind of problematic. You need to add something. So, for example, Celsius, you cannot multiply by something.
yes, so this system does not work for affine units. Yeah. The system does not work for affine kind of units like Celsius or.
Yeah,
so
It's currently not defined in the standard. So there's nobody stopping us to extend the standard and have a new version where maybe we do not have only 7 and a vector of 7 units that we extend it to describe more or give some other way to describe it that we also introduce. Currently we have only one unit system, this SI unit system. Nobody stops us from saying, okay, we become more generic and maybe define how you can define also other unit systems in openPMD. So it's currently not necessary because none of the users currently ask for this feature, as I know. But if someone is asking, since it's an open standard, you can write a pull request proposal to extend this standard, and then the maintainers and developer will have a discussion, and then maybe the next version, I think the next version is openPMD 2,
0,
2, and then maybe in openPMD 3, then this feature is defined. It does not mean what we will come to it, that it is implemented in openPMD API. So in the standard reference, how to use openPMD.
And the general way of developing the standard is that we are taking this start strict, relax later. So we are starting with this way of representing units now that does not cover Celsius, but doesn't mean that we cannot relax it later on if it's needed.
So you can have only a scaling factor, not an offset in the.
Currently yes.
And in principle, you could have also a linear transformation layer if you want to add to the standard.
Yeah, so I think nobody asked for that.
Okay.
So the standard is not really also made from the teams which are currently using it. So it's a few particle cell codes. Warp Pickle to View, Warp X, Smiley have an implementation, as I know, and I don't know all
there
of
will be a
slide. Yes, there are.
I have slides on it, so it will come. Okay. Any further questions on the unit system, or I will continue. This already brings me over to parts of the ecosystem. I will first look at a bit on the data analysis and visualization side of the ecosystem. And so this is the openPMD viewer, which is custom written for openPMD, but there are additionally plugins for other more common visualization tools such as ParaView, YT Project Visit, and there are also adapters to frameworks for data analysis such as Dask, Pandas, and via Pandas also to Rapids. All these are documented on our documentation page, which I will show later. Maybe let me take this first chance to have a quick look at the openPMD viewer, just for making things a bit more practical. I will use a little data set produced by Econ GPU.
So you can read openPMD data directly in Pandas, for example, for
there's an adapter which loads the data into a Pandas table. So the reference implementation is implemented in C++, has bindings to Python, and via the Python bindings you can then go into Pandas. I will come to the API later. So looking at this is now a data set used by Econ GPU. So again, we have particles and fields in here.
This data set is currently written with Adios as backend.
Yeah.
So you can also write HTTP5, and the file will be named different, but and the tools you can use to steer to the native file will be different. He's using currently Adios to look into it.
So the openPMD viewer is a Python package. The simplest way of starting to use it is if you install the Python package. Which you can do this way. Then you get a little binary, which is
no. You increase the content. Yeah, more.
Okay, which is this openPMD notebook that just opens a Jupyter notebook. So let me put in the path to the dataset in here. Run the entire thing. This is not something that I have written. It was been written by Jimmy Lehr, who is he at LBH?
In Berkeley with Axel.
Yeah. Okay. So, and the trick is now by having the openPMD viewer is based on matplotlib, but the openPMD viewer by using standardized data actually understands the data and seeing, okay, there are these fields in here. Let's, for example, visualize the E field at iteration 50. It all takes a while because if I look back to the data set, then it's
So it reads from disk.
it reads from disk right now.
So if I have a simulation running,
The openPMD viewer currently would not be able to latch onto the simulation that is running at the same time. This is the project that you've been talking about earlier with this with Kim Peterson, who is doing this. So it's in theory possible, but the openPMD viewer doesn't implement it.
so what about streaming?
So the difficulty about streaming is that you don't have random access to your data, and the openPMD viewer allows you to access your data at random. I can now say, okay, give me that iteration. I can say it. Give me that iteration, it will do it. While in streaming, of course, I only have data that is currently there. So especially reader code that reads data from a streaming source has to be adapted in order, because it needs to know that it has no random access.
Can openPMD collect this data and keep it in memory and accumulate it as much as I want, and when I want to look at it, when it is running?
openPMD itself doesn't do it, but you can load the data and keep it in memory. So that would be something that you would have to do.
Load it somewhere.
But actually what RDOs can do, which is maybe the opposite of what you're asking, is in RDOs you can say, I'm currently running a simulation and I'm outputting the data via stream. And I want to keep 5 output steps in memory so that a reader that is a bit slow can lag behind 5 steps. So the reader then says, okay, I'm now done with step 500, while the simulation is already at step 1000. But you need the memory for that, which is why we mostly don't use it, because
So in theory, it affects the simulation then. So when you get that point of visualization at those time steps, if you have to want to see the other time steps, it's going to, the simulation is affected as well. So it's not
necessary that you need to the memory in your main memory of your compute nodes to store all the data, because you instead of writing it to the disk, you write it to the main memory, and you have some magic handle to access this data, but this is everything then covered in ADIOS. So you don't need to care how the access looks, but you need the memory, because somewhere you need to store it. So you do not, it's not a strongly coupled system where you really directly use as data from your simulation or from your application directly. So what Isaac, for example, is doing. Isaac is really taking the byte representation of the data of the current running simulation and is not copying it. Where ADIOS, you really write files, you write your data away. But what writing means is depending on what backend you choose, for example, inside of how this layer is called, stream engine, and what engine you use to write the data. Is it a streaming engine? Is it an MPI streaming engine? Is it a file, or I don't know what else is available.
So in theory, you have to determine exactly how much allocation of memory you have to use this piece, right? To visualize a portion of the simulation, right?
No, it doesn't even have that implemented.
Oh, okay.
Only Isaac.
That's Isaac then?
Yeah.
Okay.
Yeah, but so basically, as I've said previously, ADIOS writes its data in terms of steps, which correspond with simulation steps.
Oh, I see.
And if you say, for example, I want to keep on the simulation side in main memory 5 steps of output data, so that an analysis can lag behind. This means then that you need the memory that is required to hold 5 times a simulation output.
Modern machines don't lack memory.
Yeah.
Okay?
Modern machines don't lack memory, so
Don't elect memory?
don't lack memory.
Oh, yes, they like absolutely.
Okay, maybe.
If you look to Frontier and you compare the GPU memory and the main memory, you have now the same amount you have in GPUs as main memory. In the HGPUs, you have on the host memory, but you're not allowed to everything. So you cannot simply clone down all your data to the main memory. So something like if you have the GPU fully filled with your grid data, for example, and you would like to use ideas really to store 5 steps. Not possible in the US because
it's easy to have 10. It's easy to have terabyte of RAM. No, it's no problem.
no, the problem is that if you build an HPC system, you need to take care about the power level. So for the exascale system in the US, there was a definition that they try to fit it into 20 megabyte consumer equation, and main memory is one of the power eater in the system. So they reduce most likely because to keep the power constraints.
And basically going from Summit, so the last gen system, to Frontier, the amount of main memory per node stayed the same. It was 512 gigabyte on Summit and it is still 512 on Frontier. So there was basically within one generation of HPC systems of no development there.
This is per node.
This is per node, yeah. But the actual computation that you can do per node, that increased. So we do a much larger computation now with the still same amount of memory.
Yeah.
And for being complete, Pick on GPU is a memory bound code, so memory is lacking on transit for us. But in relation to the rest of the system, the memory didn't grow.
So, but this is really also something what really depends on your application, on your memory footprint, and what you really like to do. So it could be if you say, okay, I need this, I like to use streaming and I need to store 5 steps or more, then it could be that you cannot utilize all the main memory on the system. Then it is what it is. So you need, this is a generic system, so you need to take care of what's fitting in. I like to mention, because I think there's a small confusion between openPMD and openPMD implementation. So again, openPMD, the standard is only a meta standard definition. It is only defined that you should annotate your data with special name attributes, like this unit SI, what we saw on the right side is the attributes. This now is the openPMD viewer. This is one implementation which understands openPMD data, but only with not generic openPMD data, so any kind of format. So JSON is not supported, as I know.
JSON would be supported.
Is it? Won't be supported.
Because it uses the openPMD API.
But it's JSON. Oh, I thought it's not using.
It is.
Ah, you said yesterday it's not using.
That's audio started right now. So it needs to use the openPMD API.
It can use native.
It doesn't.
Ideas. Okay, but in principle, it could also use native, the native way to talk to Adios data, but the Adios data have all these markups where each data set has the attributes, so it follows the openPMD standard. But how you read it, if you use the native API, the native HDF5 version or the Adios implementation, they also have Python interfaces to touch your data. It's up to you, you can do it, but it makes naturally sense if you wrote your data with openPMD API, then that you also use the openPMD API implementation to load your data. but nobody is stopping you to use the native way to touch the data. It will be very complicated because you need to know also because each file format has a different way to store attributes and something like that. So you need to have a lot of inside knowledge about the data storage format. Where if you use the openPMD API implementation, this is hidden from the end user.
But in openPMD standard, you do not describe how you store.
No, we don't.
It's only a description of the data, but not about how and ever this is stored.
There are additional files that describe how openPMD API stores it in Adios, because there's also not one single way of modeling openPMD into Adios, for example, but we have chosen one way, and that is documented then, but that's not saying that's the only correct one according to the standard. But if you do it according to the standard, you need to define. The standard talks in terms of hierarchical groups, undimensional data sets, attributes. So you need to define how do I map these concepts into my concrete file format. That's then your job, yeah.
So you can think of Adios has a way to store some kind of attributes, and it has a way to store vector fields, for example, or scalar fields. And nobody would stop you to say, okay, each of my attribute is a scalar field with one value, which is named has a special name. Or for example, the as unit SI systems have values, it's a vector of 7 values. You can store it as it. But Adios has also a way to have this lightweight attributes. So we choose to use this one, and so you have, as he said, different ways to implement it in Adios and openPMD API. Yeah, API is, or openPMD API is saying how it is implemented.
There are additional files in the standard.
It's in the standard, okay.
Yeah, for example, Adios is natively not a hierarchical format. So this string handling on how to represent the hierarchy is then something that we needed to add and we needed to define.
But this is defined on the Adios side more or less, on your implementation side, and not in the data format itself. Not in the openPMD standard, you do not define how you do it, it's just that you have some hierarchical data, but how it is implemented is up to you. If you do it with API, you have to do it in a different way than if you do it with
essentially.
Okay. And the definition is also not somehow written in a file or so, it is only just in your Adios or HTML5 or whatever format you should use the things defined in the standard, but it's not that you have some kind of metadata file JSON to your data which is describing what you have there. It could be, but it's not by standard. So if you do it, for example, in binary format, you have to do somehow an additional file where the descriptions could be.
If you do binary, well, that would be one way of implementing a binary format. Essentially, Adios is a binary format, so essentially they do that. But you could do it that way. You could implement openPMD in a binary format and then have an additional file that describes, okay, this is where these data are and so on. And that would be one legitimate way of modeling openPMD into binary, but yeah.
Okay.
There is somewhere, okay, I don't know where these descriptions are right now, so skip that. No, I missed that somewhere. I know I've written down. Okay, yeah. So really, this is just presenting work that I do not do right now, but maybe there. This is now a simple visualization, a 2D visualization of 3D data. So you need to select slices, for example. Can move through the slice. This is, I think, Kevin Edwards.
It's Kevin Edwards, to shear surface instability, and yeah. So I think you need to go to higher time steps.
What do you mean? Was I don't have very many time steps of the data set of this. I found it yesterday that I'm giving this, so I just searched my disk for something to visualize and found this one. Additionally, particles you can visualize as a histogram, for example, and there are one instance. Also as a 2D histogram. And especially particles are the majority of data, so it takes a while to load, but here you see it. 2D histogram. The openPMD viewer has this GUI way of using it, but it also has an API that you can use similar to Matplotlib.
Just again, sorry for insisting on this, but for understanding it's important. If I want to use this tool, I need two prerequisites. One is that I should somehow confirm or follow the openPMD standard. And the other thing, I need a plugin which can read my data format. So, for example, you have it already for ADIOS and HTML5, but if I now invent a totally different format, how I write into this, it conforms to the openPMD, but this cannot be read automatically because you don't have any description.
Of course not.
Yeah. You need to write for example, for the openPMD API and backend implementation, how to handle this new data format.
So this was originally written not with the openPMD API because it's a rather old tool already. It was originally in terms of HTML5 directly. So it has two implementations for reading. One is via HTML5 directly, one is via openPMD API, making HTML5 theoretically obsolete because that openPMD API can read from HTML5. But this way, it is currently able to read from ADIOS files, from HTML5 files, and theoretically also from JSON files, but they don't scale with the amount of data that what usually is visualized in such a tool.
How does it then, it's a bit related to this, how does openPMD handle node failure? I have multiple processes, let's say, and they were told, okay, now we're checkpointing, you get the data, but one node failed. How does it handle the restarting, for example? Does it know this data is corrupt? I look at all of it and I go.
This depends absolutely on a backend. For example, for HTML5, I'm not sure if they fixed it already. If you write your data in an HTML5 file and you forgot to close the file, then everything is corrupt. So you can't access any data. Even the tree is not accessible anymore. ADIOS has, I think, a fallback mode that is still everything what was written is accessible.
As I've said, in ADIOS, the steps are written atomically. So if the simulation crashes directly during writing, then the last step is just garbage data that is ignored.
Okay, that's good.
Otherwise, the most secure way is still the mode that I showed in the beginning, that you just write one file per iteration. That works in every backend because then you write a new file and the old one isn't touched anymore. This is the way that this data set has been created. So you see one file per iteration that was put to the disk. Yeah, but it depends on what you're doing. It depends on the backend that you're using, how it's handled in the backend.
So at the end, also ADIOS and HTML5 is using MPI analysis and following the same problems. We have this MPI that you do not have fault tolerance at all. So if your node is crashing, then you are lost anyway. Most likely your job will die because you start everything with CPI or S1 or whatever. For Pick on GPU, we do what he said. We write close timestamp where we like to write a checkpoint, and we have user implementations that we where you can say load this or this timestamp, but we have also a way where we say start the latest timestamp, and if this is not readable because we get from the API we load it and exception, then we try to use the next oldest step and the next oldest step until we found something what is restartable. But it's then up to the user to handle it. So that this is not solving any issues if the file is not written, the file system is damaged or something like that.
Yeah, especially if you use openPMD to write your checkpoints additionally to your I/O, then it's really recommendable to write one file per checkpoint so that you can handle them separately.
So do you have an automated way to restart?
it's implemented in our application, but I think all application has it because checkpointing is not easy to generalize. There are frameworks, CR I think is one of the frameworks where you can annotate anytime where you create an array somewhere or in a variable, you can say this must be checkpointed because you need really to know what is required to restart your simulation. It could be you need to, for sure all your data, your data areas and everything, but it could be you need also a single variable like that. You have somewhere a global variable as timestamp laying around. This must be updated too because you need to load it from the file. So if you would use openPMD API, you explicitly would add a data entry somewhere which is saying what was the timestamp where I was creating this file. So if it is not already in openPMD standard defines that you can reuse the timestamp because the openPMD standard knows timestamps, then you can derive it directly from there. But if you have data, we got GPU, for example, we have for the random number generators states, we have for each domain a unique entry point to generate a unique ID for particles. So on GPU, you have to pay to give each particle, this global simulation is trillion of particles, a unique ID. And for that, everyone needs to know where is my ID space where I can start to give the particles the next ID. And in a restart file, this must be there because else the simulation which is running 2000 time steps and the simulation which is running 500 steps, and then we get to start it, would generate maybe duplicated IDs because you haven't thought this ID offset. So this is really implementation detail of your application.
And the important part to understand about openPMD also is that openPMD is not a member. So what you would really need for automatic restarting, and those systems also exist, but they are completely unrelated to what we are doing, would be to have some kind of mem done, which would then really be specific to your CPU architecture, to your GPU architecture, to the way that you schedule the application to the system. While if you write a checkpoint with openPMD, that's really modeling it in this way in terms of the physical data that you are writing and additional data that you additionally need to actually restart from a checkpoint, which is in general, or basically in all cases, not the layout that you have in memory. So doing automatic restarts this way is.
But wasn't the point of openPMD to be both? So you use one way of loading and offloading data to your application back. If it's checkpointing or restarting or shouldn't be the same thing.
But in a portable way. And if you do a mem dump, that's anything but portable. And portable means that you can take a data set that you have written on one system by one team, by one application onto a completely different system, give it to a different team that uses a different application to further process the data. And that is the kind of interoperability that we are aiming for.
But that process would load it into a new system and continue from there.
Yes, but that requires that you have a common markup, a common language, which means that you at some point need to have two representations of what does the data look like in memory and what does it look like as an actually physically, scientifically valuable data set.
No, I understand, but for example, I work on a cluster, and this cluster, for some technical issue doesn't run anymore, but I need to continue my simulations in a different cluster.
Yeah.
So I guess this is the tool for, this is the job for openPMD. No, simulation checkpointed somewhere, I move my data somewhere else.
This means that you have completely different layout internally, even if it's the same simulation, but if it's running on a different system, then you have different architectures, then you have different scheduling. So this means that it's absolutely impossible at that point to do an automatic transfer on what your running application was looking like on the one system, the other system. So
yes, this is something the user needs to take care of. So openPMD is providing you a way how you can exchange. So you can dump your data on one system, go to another. But you need also a little bit to distinguish between checkpoint and normal data record. Because in a very dumb way, checkpointing, you could go to all your Fortran or C arrays and say dump it to as binary block to my disk. This is easily possible. This normal POSIX function or something like that. And if you start your simulation, which is maybe domain decomposed, exactly with the same decomposition, it is enough to say, okay, load me this binary and you into this array, then everything is fine. You can restart. But if you use openPMD, you can implement something like that you can go to another system. But as I said, it could be you need to timestamp and this is nothing. openPMD is defining maybe what I said, you need an offset for the ID or the random number generator state. This is nothing. openPMD is saying, hey, you need to have the random number generator state. This is an implementation detail of your application. So you need to handle it. But what openPMD is allowing you to throw away the checkpointing stuff. But what you can do is you have your particle simulation, what Michael, for example, yesterday showed. You shoot on a coil, there come electrons at the end house, von our side, you get electrons, a distribution of electrons. You store all your electrons into with openPMD into a file. And now you can use a particle tracker and propagate your particles you get from the first stage. So one application was the first stage, and for example, the particle itself is always simulating a few micrometers if you're lucky or something like that. But you like to maybe then send it to the undulator. Undulator. And then I will use the next stage, you like to propagate it now for meters or kilometers or something like that. Then you use another application, and now for another application, quite easy to load your data because it's defined how you store particles for the marker for a non-regular mesh.
Okay, I'll go on with that. Okay.
Question.
Yeah.
So, is this used as a checkpointing for Bitcoin GPU?
Yes.
Or so, if you restart from openPMD files or what?
So the checkpointing and I/O code is for the most part the same. There are some additional information that we need to put out for checkpointing, but basically it's the physical simulation that we use for restarting. Additionally, some further internal states, and then we have restarting routines that are specifically written for restarting from those checkpoints, and which gather the data back from the disk.
And this extra information is stored where? In what field? Because you have fields, particles, some extra record, or where this extra information can be put?
That's a bit of a to-do, let me say, because let me quickly go to
because each code has to put some extra information into the code, but which field can we put?
Currently,
we
just put it as a measure. This is not ideal. There's a current project that I'm working on and already have a working prototype for, but I will change it again. That tries to make openPMD more extensible, so you can put custom data in it. This would be the right-hand side schema. That's a current work package. Currently, we just put this information as a mesh. in future we will put this as extra information beside openPMD.
So openPMD is not dictating what you can write, but for example, this application-specific output, what is my random number state or something, maybe should not show up if I use my checkpoint what is possible and give it to the openPMD viewer, and the openPMD viewer is going then through all the meshes and everything. I do not like to see the random number generator state in the tree because it has no physical sense, and he is working on separating it where most likely this is application specific and this is normal. This is output you for your domain normally require.
As René said, openPMD describes what must be there, but it does not describe what must not be there. So according to the standard, you can already today just put the information somewhere else. What I'm currently working on adding are two things. On first, making this actually possible in the openPMD API. And then second, actually making it possible within such custom hierarchies to then use particle mesh markup again, which will, for example, be useful for mesh refinement purposes. But it's not here anymore anyway. Yeah, so
it is possible that you have like mesh time not written at each time step, but when it is really.
So for example, one very common use case is in particle cell simulation that species just leaves the observed area, and at that point you don't need that species anymore, so you don't define it. That's why the markup for in this hierarchical layout, that's why the markup for particle species and meshes is below the iteration layer, so that you can redefine it at each iteration again.
Okay, what if you, let's say, write some info so that you have decimation, so that for each step you do full, for some values, the rest you will do just partially?
That's something that we actively do and we continue to do.
It's possible. So you can always also choose if you like have one file per time step, then it's quite round because you have in this time step always the same definition. But you can also put all time step into one file, and then yes, you need to check in each time step what is the hierarchy. So the hierarchy could be changed in each time step. Maybe you have sometimes the E field, maybe you don't have the E field, the electric field. And maybe you have electrons, maybe not. And in the worst case, it's up to the application. You can have more attributes in your electrons in one iteration and less attributes in another iteration. Would be a nightmare for the user, but it is in general possible. So you need to pass your hierarchy tree again. So do I have electrons in? So, but it's up to the application how complicated it is. So, in the easiest way, you would rather say, okay, I will write always electrons in each time step, and then whoever is doing the post-processing is seeing that electrons are there, but it's not required that you do it. So each time step, as he said, also is something atomically, and something atomic, and is then self-consistent. So the next time step is independent from the time steps before.
But if I have no electrons, for example, I should send an empty array or something so that the electron could possibly exist, but they're not at this moment.
You can, but it's not required. Because
you can also say the electrons are an array of 0 elements.
So okay, so this array is already created and it's empty anyway. So if I don't send it at this checkpoint, doesn't matter anyway.
Yeah, but no checkpoints. Keep more output you like to analyze. It's easier thinking more because checkpoints, as I said, it's very application specific.
Checkpoint is output also that you want to analyze.
Yeah, but then So for example, in Pickle GPU, you have electrons, ions, or whatever the user is defining. So arbitrary kind of species, you can have derived field from species. So if I say, if the user is saying, I like to dump the electron which has output, you can do it, but I also have in the simulation ions and everything. Then you would not add in this dump also the signature in the hierarchy that there are electrons, but they are zero, because that is also not the truth. You only said you don't like to output these ones. This is not meaning that there are no ions available. So, but this is then also again domain and application specific, because what does output also mean?
Should continue your bit?
Yeah.
Okay.
Just another question. So for, let's say, simple 1D problem, which is different like Wakefield, 2D, large, we do have a huge number of time steps, but small a number of quantities. So having a huge number of directories for, let's say, each time step, this could be like ways of
The iteration label doesn't mean time step, it means checkpointing iteration. Snapshot.
Using one file per iteration is just one of the possibilities. If you actually have very, very many time steps, then the layout that I would recommend using is the one that Adios has with its steps that are contained in one file.
It's nothing you need to choose at the moment where you implement openPMD. You can choose it at one time.
I will show it. Okay, just quickly, we've seen the data analysis and data visualization side. This is a short part of the list of simulation codes that currently use openPMD, Pick on GPU, but also WAPX, FPPIC, SimX platform, WakeT, HiPace+, and so on. So many different institutes are already on there. If you are interested in projects that are using openPMD, writer and reader side, we keep this updated on our GitHub site, so if you're interested, go over there. Not going into detail on this one.
You also have codes, one pick code dealing with this.
Mala, for example, yeah. We've recently added it as well. Then extensions, we've talked about this already, so I think I don't need to say lots more on this. But basically, for example, here you see again in the attributes, current deposition, particle interpolation, such things that should be standardized if you want to output data, but that should not be part of the generic particle mesh standard. So those you put in a standard extension. Currently, via attributes with this work, which I've just talked about, this possibilities will be more, because then you will also be able to use custom datasets and custom hierarchies. Yeah, these two slides are, I would say, more politically important. So fair data. That should be findable by having standardized metadata, accessible by being open standard, open source, and openly developed.
Are these required or are these optional? These attributes, for example, do you require them?
These are required.
Yeah.
There are optional attributes as well, but those are clearly defined in the openPMD standard. This is a required attribute, an optional one, so on. So I think software version software is actually optional, but I don't recall.
We need to look up in the standard. I would say maybe all of the three are optional.
Might also be, yeah. So there are required ones and non-required ones.
But nice to know who you can blame for the data.
Yeah, it's necessary, absolutely. This is my question. I think it should be required, otherwise it doesn't make sense. Also, something like license or whatever should be somehow required for this.
License is a good idea, we haven't done yet. Might want to have that.
Yeah, our data department was this data that doesn't have a license, you cannot talk.
Since there's a short format we have in Alpaca how you define licenses. There's an automatic way, there's a definition nowadays that you do not add full license code, but I can show it to you later on.
Okay.
There are no short symbols for licenses.
And interoperability, we've talked about this already. That was the major motivation in the beginning. Reusability also. Find a data set somewhere, you don't need to go hunt down the original author, but you can reuse it directly. Heading over to the reference implementation of openPMD API. The major sites to go on for using them are the read the docs page and our GitHub page. So we try to keep an extensive documentation and also try to have packaging for the most common package managers, or if you also want to, I prefer normally building source, of course. And the software stack that you will end up using if you use openPMD is this one. So on the left-hand side, the topmost level is your application code, your data writer, your data reader, which describes its data workflow in terms of openPMD. And then, the easiest way, you just pick a file name extension, but I will show a more in-depth way in a minute in order to pick the backend. So if you put .h5, then you will by default create an HD5 file. .bp, that will by default be an Adios 2 binary pack file. SST is for sustainable staging, transport, and streaming. JSON is JSON. And on the bottom layer, you have the actual transport and storage that you use for file I/O, regular POSIX, MPI I/O, which gives you then access to parallel file systems, or for streaming purposes in InfiniBand, for example, or now on Frontier HP Slingshot. Or
so a quick question too. Does all the I/O backends connect to all of the data transport storage?
No, not all of them. So that's for example why I put these one in dots, because Jason and Tom just write to file system. Yeah. Streaming is via Adios 2. I also think I have another hidden slide. I have the same overview for specifically for Adios. If I find it, that one would be over. Oh, that's in my presentation. Yeah, this is what it would look like when using Adios specifically. So Adios itself then again has different engines, which is for files binary pack engine, for streaming within RDMA as a remote direct memory access contexts, or via just TCP as fallback. SST for streaming via MPI with yourself, what we talked about earlier for load balancing, that would be SSC. For wide area networks, there's also Dataman. So these are the options that you have in Adios. For HD5, they also have, of course, their I/O workflow, for example, defined via MPI I/O. So the last layer really depends on the backend and what they support and how you configure it.
But there are some meaningful defaults. So if I do not choose anything, then it is using MPI I/O or POSIX I/O, whatever is available.
Yeah. This is also one of the core points of openPMD, that we try to have same defaults. For example, last year there were lots of performance optimizations in HD5 where we just added defaults that are known to be performant by default and useful by default. But if you actually want to configure it specifically, because you know that you're using Adios and you want to actually have that number of aggregators and not this number of aggregators because you're running at that scale, not at this scale, then you can configure by.
Do you talk already about compression and so on? Is it coming or?
It's coming.
Okay, then I will not say something.
It's coming in the manual session.
Okay, then I will maybe say something again. openPMD API is not stopping you from tweaking the backend you're using behind. So if you use Adios 2, you have a lot of possibilities. You can enable compression. You have billions of compression libraries integrated, so layers integrated. You can have lossy compression, lossless compression. I added loss into Adios that you have parallel compression. So you can use set standard from Facebook and these extensions maybe need parameters to tweak you. So once you need to say what compression algorithm you like to use, how many threads you like to use. This openPMD API has ways that you can give this information which are backend specific to the backend, and it will then hand it over to the backend, so the backend can understand it. And say something if I say something wrong. Since configurations are really backend specific, they're not generic, so you can't use the same for HDF5 and the same for Adios, because HDF5 maybe don't understand that you like to use BLOS. But there is a way that you say that for example, you write out electric field and magnetic field, that you say, okay, magnetic field, if it is written out, it is always compressed. Each of the values is bit shuffled, so there's one optimization that you rotate the bits, that the compression ratio is much better. You can give a JSON description that you say, okay, if I use Adios, enable for this data set, so for my magnetic field, the compression, and in HDF5 do something different.
The dataset specific compression that you're talking about, specification that you're talking about, is still currently on GPU only. That's been on my list for a while, so this is something that we have prototyped in Pick on GPU, and now someone will need to implement it, maybe, but not yet. So you can do it manually in the code by saying, okay, at the time when I define my E field, then I add this compression operator, but that's something you will need to code currently. The way we have defined it in Pick on GPU gives you the option to just specify it at runtime.
So, okay, fine tuning is possible, but not on that level yet.
Okay. I'm not trying to give a programming introduction right now, but I will just quickly show some key concepts of how openPMD works and how writing data with openPMD works. I usually do this in Python, but given that we actually have this at the simulator workshop, I think C++ is more interesting. There are also recently Julia bindings for openPMD.
And there are no formal bindings.
No.
Also not in the US.
So there's a GitHub issue that we have on as a survey on what languages would be interesting for the community. And actually, our most recent GitHub issue is someone asking for C bindings, and you're not the only one. The Julia bindings, let me say, the Julia bindings are an external contribution by someone from the University of Toronto who just was interested in doing that. So at some point, if you're interested in contributing, we definitely are interested in working with you.
There might be something which you could do in the framework of this project.
Yeah.
But I don't know how complicated it is now.
Yeah. I mean, the normal way to go about things like this is define a private interface that private C interface that you use for your application in order to talk to openPMD. And if it actually turns out that this is something useful for the greater community, then we can. So this is what we want to work for. Definitely something. So I'm definitely agreeing with you that C bindings would be useful, but someone needs to do it. So currently C++. This is just one loop now that pretends to be a simulation. So I'm just doing 100 time steps, and each 10th time step I pretend writing an output. So the root level of openPMD, as we see here on the left-hand side, is serious. So you would initialize openPMD by giving the file name that you want to have. Then the extension I get from the environment, so just let me put that here. Then we want to create the dataset, so the access mode. We are using MPI for this one. This was also something that we talked about, that openPMD is MPI aware from the beginning. So we pass an MPI communicator, which I defined up there. And then what he just talked about, the dynamic runtime configuration. So you could give it inline, or you can use this syntax to refer to either a TOML or a JSON file. TOML is more readable, so we use that.
But I could not just give only the data to the file name, this extension. Or would it also work, and then it chooses some meaningful default for the But just give the file name and the extension. It should in principle be enough to define it, and then I hope that all the backend is chosen correctly without any.
File name and the access mode, that would be enough. The other two, so the MPI communicator and the JSON configuration and TOML configuration are optional. So let's now write mesh data and particle data. This is just defining some attributes. And as I've said, we can also define custom attributes for custom domain-specific extensions. For example, just write anything here. Then a custom attribute, so key and value. Then we define the electrical field. So meshes E field. And some of the required data, they are pre-filled with some default values, but since we are writing something three-dimensional, I'm specifying axis labels, offsets, and so on. And here we write the actual data. And the important bit now is that first I define the global size of the dataset. So field component reset dataset, I specify now the data type, which is define some field data type. Yeah. And then additionally the extent, which is the global extent over all parallel instances. I've defined up here, so the grid size. And after this point, I store the data, which I have here initialized as a unique pointer. Supported are unique pointers, shell pointers, raw pointers, and STL containers. So I say field component store chunk. In this case, I'm using a unique pointer, so I move it into there. Unique pointers have the advantage that the backend might be able to use the knowledge that it's the sole owner of the data to do some optimizations. And then the current offset and local blocks that local block extent. So this is the part that we've now defined, the global size and the local size of the block that we are writing. So we already have a look at what this does. Quickly check that the configuration is okay, yeah. Okay, so I do MPI run, binary, and now we have the simdata.ep, which is an RDS file. So for now, we've only written the mesh data. This is only the array data that we see right now. Let's additionally print the attributes and restrict the output to just the 19th step.
So what does it mean now? This, for example, you have this line. First is the data type of the quantity that I'm writing, then the name more or less, and
then the global size.
Global dimensions.
Yeah. So if I additionally print the attributes, we see here, for example, the custom attribute that we just set. I'm a custom attribute. And the further standard defined attributes. For time reasons, I think I will just copy over the particle side from the solution. Or I will just show the solution right now. I also have this on our local GitLab. If you want to look at this file more in depth, I will put it on the whiteboard in a minute. The maybe interesting part here that happens, so for the particles I write position and position offset. It's basically the same again. I define the global size. Here for the particles, I need to know, okay, which I've said previously, which is my actual chunk, which in general you will need to do some API communication for. Here with this minimal example, I just know what my chunk is. And for the position offset, this is something that the standard requires, but you might not actually need it because in lots of situations you might be fine with having just the position and not need the position offset for numerical reasons. So if you have a data set that you want to define, but it's actually constant over the entire domain, then you don't need to actually define it, but you can replace it with just make constant here, which will then replace the n-dimensional array with two little attributes, one giving the shape and one giving the value. So let me run this one.
Could you probably go back to the code? So at the beginning, what he showed all the time is the description, what you like to write, you pass over the pointers or the data or the container to openPMD. But at the end then, if you have everything described, you need to say that the series is flushed. So this will then really be the operation, and the API is also defining what flushing means. So at the moment of flush, what
is
this meaning?
It depends on the backend, but what the only promise that the API itself can make is that at this point you can reuse the buffers. So this is something that I didn't go into detail right now, but in the top example is that I'm using unique pointers. So this semantics of being able to reuse the buffers does not apply at that point because the API knows unique pointer, I'm the sole owner, so I can do whatever I like with the data. But down here, I use an STL container, which openPMD does not take ownership of. So I need to flush before the STL container goes out of scope. But generally, I/O actions are first enqueued and then flushed at some point. This first just means that you can reuse your buffers on the application side. And when data actually lands on the disk, it's then backend specific, because basically in RDOS it's impossible to dictate when this happens, but instead it just happens as soon as you close the step. Or in terms of openPMD, if you close the iteration. This is then the point when you will see data on the disk.
So flash is actually required each time step.
You can theoretically leave it out also just close implicitly flushes. But at this point, because I'm using an STL container which goes out of scope, I need to flush at this point, because after that the data is invalid.
So think about you have a simulation and you have an electric field and you like to dump this electric field to describe it, how large it is, and then you give openPMD API the handles or the pointer, for example, to this electric field. And if you not call flush and not call close, and you go then to the next step, and then the simulation field get updated, you haven't written anything. So you overwrite the data, and if you later on close the file, then the last change will be seen in the file. So with this flush, you get the guarantee that the openPMD has somehow used your data and copied it into a separate buffer, created a double buffer, flushed it to the disk, or it is not guaranteed what it means, but it is giving you guarantees that you can overwrite your data without losing the data you like to write to the disk later on. So it is not saying when it goes to the disk, or maybe if you're streaming backend when it is flushed out to the world, but it is guaranteeing that you can overwrite your data in your simulation.
Just quickly about up. So the example that I've just shown is on that page which you are seeing right now. Let's see. Just again. What's the theory? Ah, that's already push 5.8 openPMD the specific example. So if you want to look at it more in detail, then C++ MPI is right.
openPMD minus CPP minus MPI minus example.
Okay. I think I at some point also put this on the documentation. Yeah. Now what I actually wanted to show mainly is I'm currently writing the EP file. So let's see it again. But I've been writing one file for now. So what if I want to write one file per iteration? What I do then is specify that as part of the file name. Just write an expansion pattern in here. In this case, it was just a minute example quickly recompile. Normally, you would expose this as a runtime option, and then run it again. And we're now getting one file per iteration. File extension I actually have as an environment variable, so let's do this as an HDF5 file. If I run, it's exactly the same code. And suddenly there are also HDF5 files in here, so I want to look at one of them. This is now one iteration in HD5. Just specify the runtime. You can also use openPMD as an openPMD based tool in order to open or access a data set. And I will use this as a link over to streaming, because then we quickly compile the old one again.
Just a question back to the source code.
Yeah.
So correctly, what do I need for writing over? So it's clear at the beginning you have to define the series. Then at some point you are taking this current iteration, you're creating this.
Yeah.
And then you have a lot of other code. Is it always necessary for each time? And I would expect something like I define everything in the beginning, for example. So I need just my grid, which does not change during the simulation. Then I just say write this array, and this is just one code per iteration, and perhaps flush it.
This is that code. This is defining the attributes for the field. This is defining the attributes for the iteration.
Which is just outside of this outside of the iteration.
This is in the iteration.
Oh, you can put it outside. You can also, but you need to say each time to openPMD API for each data set what are the properties, because they could change. So extent definitely change. Unit maybe is not changing, but nobody is saying that you not do a renormalization of your system during runtime. So it could be different. In most cases, it will not be different. And in that case, most likely you will write a helper function where you say, okay, for the electric field, I always set these properties because I know that it's meters or so. Pick on GPU, where a lot of buffers are self-aware what they are. We have a lot of traits where we can ask, put in a buffer and ask, give me the description for openPMD, and then the 7-dimensional vector for the unit size is coming out, the unit conversion factor is coming out automatically, and we can generate this code. So we do not need to write it each time, but it's then again implementation specific.
But you have to call these functions more or less. You can write in the function is always creating the same list, but you cannot define global attributes. For example, having the mesh as a global attribute, which is over the whole simulation, always the same, and I'm just putting the data somewhere else in each iteration.
But if you use the variable-based encoding of Adios2, which uses steps for encoding the iterations, then it will end up as just one attribute, which might then change change its value.
But I think the question was more: can I define once that I have all these properties and then say that the data changed, the data changed, the data changed only?
Just cut out the data without any description. Descriptions done in the global section, something like this.
But as I know, certainly not the case, because it's again domain specific or application specific that you can.
Yeah, but this kind of global section, you effectively get to use this encoding of that Adios has.
Yeah, but it's only then for Adios. But speaking in generic openPMD API, this is not the case. You need to describe it anytime.
Exactly. So it's been a design choice to put the particle mesh markup below the level of iteration, and that's where they're defined.
But that's just a waste of more or less space if you write the same data each time. It's a mesh doesn't change, but you still write it each time, so it's just you can do it, but it takes time and it takes space.
Oh, if you don't like to write the data, you don't call all those functions.
I mean,
you just write it the first time step, and then but this is a bit logical.
But if you have only the data in the first time step, then you only put it in the first time step. And all others don't have the data.
The data is valid for all time steps, but it doesn't change.
What does the actual data contain in the mesh? That won't change, right? So the
data per data point, each grid point it changes, really, but the grid point itself, the position doesn't change.
No, yes, and in relation to the amount of data that you have in the n-dimensional arrays, attributes are
It's
small.
one scalar per point.
It's come in?
Per grid point, it's one scalar.
No, but you define the attribute. So
No, I think the question is more
example.
going into the overhead. You need to write the code or call it always one.
Yeah, it's one is.
Why you not give the definition only once and then you can say, okay, the field updated and then.
Yeah, that's as I understand, normally you write the mesh for each iteration, for each snapshot more or less. The question is just, can I avoid this if I don't need it?
No, it's not an API interface, but this is something you would most likely write for your own application.
Yeah, we can discuss how to do this in a way.
And that is the data that is required for one mesh. Yes. So for the entire n-dimensional arrays that you have here, which in this case are three-dimensional arrays, you have additionally, what is this, 12 attributes, which are not defined for each single entry in the n-dimensional arrays, but there is one attribute, or there is one relatively small attribute of sets for the entire mesh. So they don't scale along with the grid points.
I think the question was if this information is being written every time,
It's repeated every time.
Yeah,
This is snapshot 9,
including the position of grid points.
So, because they are more than each snapshot is atomic. So therefore it could be changed each snapshot. Therefore you are required to provide this knowledge.
But you somehow have to write the position of each grid point, because if you have an unstructured grid, for example, then you need the exact coordinates in the three-dimensional space or five-dimensional space of the grid point. So this needs a lot of data. You write it for grid point.
This method at the moment does not specify unstructured. It is type other, right?
Oh, but if you have answer, you can represent the unstructured grid with particles, maybe.
Yeah, for unstructured grids, that's something that, as you said, is currently not done, and if you want to do this, would be something that we would need to look for a good solution.
So at the moment, you just support Cartesian grids, structured, equidistant Cartesian grids.
There are 2 or 3 further modes on top of Cartesian, but Cartesian is a default. Yeah.
And also equidistant.
Yeah.
Yes.
Currently, yes. So if you really have a use case where you repeat lots of information each iteration, that's the point where we'll need to sit together and look for a solution for that. We currently don't have that kind of use case. Okay, what I just also wanted to show, if I now change the engine type to SST for sustainable staging transport, and additionally said that we should just use some default networking techniques for streaming, then I start the code again. And I create this. Okay, then it will for the moment do nothing because it's waiting for a reader. There is a little file now on the file system simdata.sst, which just contains some networking address depending on the actual transport that you're using, in this case sockets. So if I open this now with openPMD, I have on both ends used the same implementation now, but the backend was now a streaming one. And are they finding each other? Yes. And it works the same way. So this is a bit of what we are trying to do to keep this kind of configuration and specification of how I/O is implemented in the backend, a runtime property. Also here you see, for example, the compression, which I've just been using the whole time now implicitly, and without even noticing it. The only way to actually notice it if I write just something in here which it does not recognize, that we see. Change back the engine name. Then Audios will complain it doesn't know this compression method. So that's really the only way of proving it to you that I'm using compression load. Otherwise, using compression is basically transparent to the user. Given that I'm already a bit over time, I'm not going to go further into detail on this live coding thing, except...
Let me only repeat once what you did. Maybe it was not really visible. So he was really now, instead of writing to a file, writing to a socket, as the simulation starts to write. So the simulation starts to write and waited for someone who is consuming the data. Then he was using the standard tools openPMD API is providing that you can have a short look on a terminal into your data. And he was saying, okay, open me, he had a file which is giving the information where the data can be dragged from. He was using this, and under the hood, he was also compressing the data. So he was writing this data area. Adios was then hopefully shrinking it with the compression. Compression does not require the data at the end smaller, it could also be larger at the end. Was compressing it with blood, and on the other side he was consuming it, and he hasn't seen that the data was compressed. So it's absolutely transparent for the user that he's reading compressed data. So you do not need to take care, oh, how do I need to use now how I need to interpret my data, if it is compressed, how I need to do it, if it's not compressed, have many if defines maybe in the consumation code that you need to handle compressed data, non-compressed data. This is everything Adios is doing for you. It is this compression stuff is not Adios only, also HD5 can do it. My personal feeling is that it's much easier to use with Adios.
It's actually near openPMD not implemented currently in HD5, but it could be. Yeah, so basically I've been reading now not from a normal file anymore, but instead from a compressed stream.
And you could also read it from two readers. It's not required that you have only one consumation thing. So you could also start two applications and both reading the same data. So send it to your visualization cluster, send it to your I/O sync, which is dumping it to the file, and maybe send it to your Jupyter notebook and consume it there and do some dynamic like this.
Yeah. Additionally, for example, what I could also do, currently when I'm writing this file, then I see that the data that I get from this is the actual data file, it's one file. But I could also use the Adios runtime parameters now. Where was it? It says num aggregators and say, okay, I'm running with 4 MPI runs now, but I want 2 aggregators instead of just 1. Now, I'll compile it, that was the trick. Now let's look at this again. And there's data 0 and data 1. But the it's still, so you're aggregating two files, that's an implementation detail. The actual data set is still one file, which in iOS is implemented.
This different aggregator, so you can in principle write the mean value to one and the sum to the other one.
Oh, this aggregators are how Adios is handling if you set to Adios right.
It's not a data transfer.
Yeah, write each file for each one file per aggregator. You can say how many. So you could have a cluster with where you have one node with 8 MPI rings, for example, and it most likely does not make sense for performance to write with all 8 MPI rings on this single node to a file. So you can aggregate it locally first. You can say it, and then only one API process of this node is writing then a file to a disk, or maybe it's a shared file. You can also have still one file on a disk, and then only one producer writes really data. Because if you're on Frontier or something like that, this is what's 60,000 GPUs, and you start an API per GPU and you write data. It will not improve your performance. It's the opposite is the case. If you write with 60,000 MPI ranks to this, so it makes no sense. So if you write with one MPI rank per node, it could be much better. Maybe you need to aggregate it more. So, but this you can select at runtime, and this is really system dependent. System dependent.
So this performance optimization is especially necessary at large scale, and the important piece is because it's system dependent to have it as a runtime configuration option so that you can actually experiment and have a form of performance portability in the I/O system. That's what I wanted to show.
It does not work then as a reader, so you can still then copy over the data from your large HPC system to something smaller and analyze it there. So the reading performance will also depend on how much files you have and on your system architecture if you consume it in parallel.
Okay. I just have some few slides to end. I will mostly skip through them. This is one slide that I stole from Axel. He's using openPMD in WarpX, and I just wanted to show this because in WarpX, that's actually the code where they have mesh refinement. So if you're interested in mesh refinement, then due to Zoom being overlaid, you can't really read this, but there is an open pull request in the openPMD standards. So
I just commented on it.
that sounds good. Okay. Yeah, this was maybe more for mentioning that it exists. Yeah, generally, one trend that we have been countering and trying to develop solutions for is that really I/O at the large systems does not scale anymore. Even if you just look at the development from Titan over Summit and Frontier, the compute performance grew at a much higher rate than the I/O performance did of the system. So we're at a point where I/O basically already does not scale anymore. In bandwidth and in capacity, and we are observing similar trends in experiments, which is what Michael mentioned 2 days or yesterday, I think. And we're also dabbling with experiments a bit. So one thing that we're trying to have this more scalable is the use of streaming. The idea there is to have the simulation running at the same time concurrently with an analysis. And instead of going the detour via the file system, use, for example, on Summit InfiniBand in order to stream data directly into the data consumer, basically the same way that I just showed. And that's the setup of the experiment that I did there. But essentially, the takeaway is Summit had around 4,500 nodes. And I was able to run a simulation that ran into the parallel file system bandwidth limit, 2.5 terabyte per second, at a bit less than an eighth of the system. So after an eighth of the system, I had already reached all the throughput that it can give me. With streaming, I went beyond the parallel file system bandwidth limit, so that helped alleviating this problem a bit. Skipping over this one. Yeah, it's still important that you correctly configure things then. So if you have an application writing data and an application reading data, so how do you move the data from the writing application to the reading application? That's not trivial anymore. So you have to somehow think about a good data distribution. Also, the implementation is important. What I just showed you now on my laptop was based on standard networking techniques, which did not scale at all. So I really had to use the InfiniBand. So there are new challenges that come from streaming that are somewhat relevant also in I/O and Fire I/O, but not so much. Yeah, this is also an overview on some further benchmarks that we did. So Axel did an research on the effect of compression, because compression can affect I/O performance in two ways. Compression takes time, so it might reduce the I/O performance, but it also reduces the data, so you're faster to write, so it can improve I/O performance. So are you going to be better or are you going to be worse? Answer is, it depends. On the system, on the data, on the compressor. So you can use compression in order to speed up I/O, but you have to do it correctly.
Correct.
Yeah.
What type of compression is used for flowing point data?
I think you
in that case, you have different compressors very tiny at the top. So different colors are different here. Set standard is from Facebook is for us giving the best compression for floating point, for example. But also then with some pre-filters that you say, for example, bit shuffle my data, so that the highest bits get collected from n values together, and then everything is compressed. But for ideas, for example, you can choose it at runtime what compressor you like to use, what transformations you like to use. So also BLOS has developed in the last, I think, 3-4 years a lot, and they added a lot of new compressors, new transformation layers. You can choose it. What is good for your data, you need to test on a sample data set, or you need really to observe by yourself, because there is no generic way. But you have also ZFP is, I think, lossy compression. Adios is providing also a lot of lossy compression algorithms where you can maybe say, okay, I need 6 digits, and this is representing my quantity well enough. So you can enable this one, and they have different speed, and this could be that then your node needs more time to prepare the data before you can write it to this. But you need to think about it's absolutely system dependent what is good for your current system. Therefore, it is again a possibility you can choose at runtime. If you're on Frontier and you have 6,000 nodes, I think 6,000 something, and you have a theoretical bandwidth of the file system of, let's say, 12 terabytes. It's a little bit above what you can really reach, but we are optimistic. So you have, you need only 2 gigabytes per, is it correct? Yeah, 2 gigabytes per node to utilize your system as your file system. So 2 gigabytes produced from 8 GPUs and then writing out per node, this is nothing. You have plenty of time if you compare it to your main memory bandwidth. You have plenty of time to prepare your data to use what I always call serialize your data or transform your data before writing it. And maybe in a good case with that standard GPU, for example, it depends and also on how what's your gradient of your data and everything. But it's easy for us to reach a factor of 2 in compression. Then you write only half of the data out, and then it can make a huge difference, because if you use half of the memory of all GPUs in Frontier, and you like to write a checkpoint, you are up to nearly 3 petabytes of data. And even with this 12 terabytes per second, it takes amazing long. So if you then can reduce by a factor of 2 your data while compressing, and you need maybe then a few seconds to prepare your data for compressing, it's hidden. But it's absolutely system dependent, application dependent, and compression, you know, most likely is also not easy for floating point data. If you have maybe a lot of integers, it's quite easier for the compressors. But therefore, you have a choice which compressor you like to use. And if you use the compressors, for example, in Adios, you can define a different compressor for each data set you're writing out. So if he was selecting it now via the common file, but you can also hard code it in the moment where you write out, you define your data set. I like to write out my electric field. You can say, okay, the electric field will be written out with a loss compression and set standard, and the magnetic field X component should be written out without compression, but the Y component should be written out with LZ4 compression, for example. So you can mix it, and at the end, you consume it like your data is not compressed at all. You don't see it. So it's a poor optimization. So bandwidth optimization, size optimization for your disk, it's very often a limit. And yeah, that's what you can do, but you should not decide at the moment where you make your application large I/O already, what you like to do in the future. So this you can choose later. openPMD, API, Adios, HD5 bringing you the possibility to do it later, but you need first to use some abstraction library to have the possibility.
Okay. Then the trend that the parallel file system bandwidth limit was reached very early on is also confirmed on Frontier by WarpX by Axel, where they also ran into where they were able to use openPMD with Adios 2 in order to actually make use of the basically entire bandwidth that the system has. This one I'm not going to go into detail on. It's a research was done by Lipeng Wang on the impact of how you write your data onto reading efficiency and strategies to reorganize data online using streaming. Yeah, so if you're interested in using openPMD, GitHub, read the docs that are the first places to start. And I think I've taken enough time by now, so thanks for giving me the chance to present this here. And if you've got any more questions, want to discuss, then feel free. Thanks.
Last question. In Beacon GPU, do you use dispatches or checkpointing to be able to put the particle back in the space?
We use it, but what I said before, we currently do not support that you restart it with a different domain decomposition.
But the same domain.
It's the same domain, and we use it to find, since we have a large linear area of particles, we need to know which offset we need to read from to recover our domain. So this, for example, bounding box is stored inside of the patch. So bounding boxes for patches in openPMD can also overlap. So you can, if your application has some really strange pattern, maybe what Plasma has because of the load balancing, and you do not have rectangulars, or something like that, and you have some stitches somewhere, then you can define the large bounding box, and the next bounding box can maybe overlap. This is because that you reload it, you need to take care that you then check is really each particle in my strange real representation of the domain located.
So, for instance, the idea was also trying a bit about talking about this is fine for the openPMD, but this is mainly about outputs. So the question is a bit briefly, how do you handle your input to your code, like just user configuration files or whatever? So you mentioned this pygmy library at some point. So
Yeah.
Is it what kind of format is it?
Pygmy library is something like openPMD, but it's the standard for the output. Do we record still? Do we need to record? I think it's only. Yeah, maybe. I don't like to say that wrong.